Hello everyone, this is another project I've started. It's a digital caliper interface so that I can read the output of, let's have a look. So I can read the output. See, the screen's knackered on this one here, look. But basically what's on here, it comes out of here and goes through my interface here and off to my PC to an application that I've written. We'll come to that in a minute. So it's on a long cable so we can use it. I just want to say that not all calipers have a data output. This one does. This is my small vernier. Well, sorry, digital caliper. It's not a vernier, it's a digital. So you have your normal. If you could have a good look, let me see if I can get this light right and get it zoomed in. Right. Yep, here we go again. I think that's about right, that, isn't it? Yeah. So you can see, you'll be able to see on your calipers. Usually there's like an arrow. There's the one for the battery, and you've got another arrow there. I don't know if you can see that. There. That indicates that there's another opening there. So just so you can check. So you just slide that down, and it comes off, and there's your battery underneath. And then if we just slide it back, I'll tell you what, I'll just leave that off. Then I'll take the battery out, and then you can see that there's another one there. If you slide that up, it might be a bit difficult and hard to see. I usually get my nails underneath, and it comes off, and then you can see, where are we getting the light? You can see that there's four contacts underneath there, and if I take this, I'll just mention that these batteries are not rechargeable, so you need to remove them when you're sticking this interface in, because the interface is providing 1.5 volts. So I'll just put that in there if I can in camera, and you can see there that the digits have come on there. Now, depending on what calipers you have, I'll just open it up to about. I don't think this set has it, but if I open above about 1.5, and I'll just reboot from the USB, and we'll find out. But yeah, so if I just zero that, I don't think that's got in there quite well. Hang on, let me just give it a wobble. I found that none of these connectors are the same. Let's see if we've got the connector this time. No, I haven't. Yeah, come on camera, and then just while you're on camera, just call me a liar. Just don't want to push it in too far, because there's also some things in there, components. Oh, nearly had it there. Oh, there we go. Anyways, you can see it on the. Oh, no, you can't. Oh, get the light out of the way. Can you see it now? I need to get some light in. There we go. Yeah, you can see that it reads what's on there, The calipers are saying 12.22 and my display is 12.22. You can see they're both the same. And I'm not going to try, I'm going to get rid of these small ones. Like I say, this connector it's a pain in the ass. It looks exactly the same as the other one, but for some reason my plug doesn't seem to work well in this one. I'm going to sort it though. So yeah, I just wanted to show you that you may have a hidden connector on your calipers. That's all I wanted to show you with that. So I'll just yeah, this one's been a right twat. Right, we're 0. Come back to that. Got this. No idea why that is playing up like that. Seems to have sorted itself. Well, it had sorted itself out. Yeah, there we go. We're back to normal now. Temperamental things. Yeah, so here's the big one. This is an old one. Someone swapped out my new one for this. What have I just done with the cable? Oh, there it is. Hang on, what is it? Have I just tangled everything up? Right, yeah, so, yeah. Seems to plug alright on this one, okay. So, he says, now that I've had it in the other one, let's just give it a reboot. You asshole, there we go. Well, yeah, I have no idea where to get these proper plugs from, like, so I've made one. This is made out of an old phone socket. I've done an Instructable showing what I've used, and I've just carved it to fit. So let's just see if that actually does something. And we got some contact. Oh yeah, there we go. Right, so zero that in, and that should zero on there. Can we see that again now? And if I move it open, there we go. So although it's no good looking at the screen on here because half the digits are missing. It needs zapping with them little lighter zapper. Anyways, so you get the idea. So we've got an interface, and this I'll just stick that there. That might be. Can you see that there? Oh yeah, sort of. I wonder if I can get a bit more contrast. Oh, that looks better, doesn't it? So yeah, we can see that now, and like I say, open that. Now, I don't know about all calipers, but I found out with this set of calipers, it has like a calibration thing, and I wanted to show you that. So what I do is I usually open up to just above a millimetre, and I reconnect the power by via the USB, and it boots up. And then what we can do, we can check like a calibration block 6mm. You can't do it on the screen itself. What you can do is use the software that I've got. I've written some software that, so this LCD is like an optional thing that's going to be, you can plug in if you're building a machine where you want an external display. But the reason I've done this interface is so that I can see it on screen on my computer. So I'm just going to bring up my application, like so. There we go. So I've written this little application. I'll put it there, and this is currently this is currently plugged into COM port 4. What I'm using at the moment is something similar to one of these. It's just a UART to USB, and this is connected to my STM8 on the UART pins, and it goes to this, and that plugs into my USB port, and it comes up as COM11. So we just connect COM11, and then we can see now that we've got here the readout, the same as this readout up here, and the same as the readout down here on the calipers. So we've got three choices. We look at the calipers, we look at our LCD, or we look at our PC. Now I've made this application. Not everybody will want both metric and imperial, so if we just double click metric, it'll just show the metric one there, and we can get back, double click again, and if we just want to see the imperial, we can click the imperial, and it'll just show the imperial. What we can do also, and as I was saying about the calibration, once we're connected we have this cal button here. Now, like I say, I don't think all calipers do this. It happens to do it with mine, and I think this sort of caliper, this size, is used in it's a Chinese version. It's got the Chinese protocol. It's just two 24-bit numbers that come out of it. But one of the 24-bit numbers is for calibration, and I think this type of vernier is used on, you know, inspection units in a factory somewhere where it's permanently connected to a computer, and you can see the actual calibration. So if we click this button here, you can see that with the calipers closed, it's reading something like +6 mil, and the idea is, oh right, so if it's below 6 mil here, you can see it on the metric one. Let's just have the metric. Oh no, hang on. Oh, I can't do that. So I've got to close this before I can use the other one. But you can see that we're at 0 here, but on the calibration it's around 6 mil here. And what you do is you have a calibration block. You have a block, something that you know is exactly 6 millimeters. Well, I had this printed out on my 3D printer, and I printed it 6 mil thick, and it is 6 mil thick, believe it or not. So what you do is you stick your calibration block in there, and it should read 0 if it's within tolerance, and you'll either get a plus or a minus number, and that's what you add to your readings of 6 mil. You can see that I'm actually reading 6 mil here, but here it's 0 because this is for the calibration number. So and if it was above 6 mil, so if I keep going higher, so if I increase that, you'll see that it is actually reading a negative number. The higher I go, it's going minus. If I go below 6 mil, it'll read a positive number. So I get to, well, put that in there, get to 6 mil, and then if I go less than that, you can see that it's giving a plus value, and it's going up the closer I get to the jaws. So that's what that is for checking the calibration of your calipers, and mine are spot on. I can't get any closer than that, can you? So yeah, so that's what I've added to this software that I've done. So close that. I can move this again now. So yeah, so it's actually reading 6 mil, and also this value here always on there. So if you are going to something like measuring that, and then you 0 it on that, you will also 0 it on the readout. This readout is whatever's on this readout. Now also on the imperial, just put it to 0. Right. So yeah. So some things might be in like that. Some things might be in inches, and you can see that that's 3/16ths of an inch, which is 0.185 something is that. So I've also made it show the fractional value of this decimal value, and it shows you that value when you're within 0.005 of the fraction. I just thought it'd be a handy thing to have. So this is what I'm working on. I've done the PCB. I've sent it off to be made. I'm just waiting for it from PCBWay. So once I get the PCB, I will show the fabrication of that. But what I'll do now is I will just pause, get rid of this, and I'll show you the circuit and just explain what I'm doing in the circuit as well. I don't know if anybody's interested, of course, but we'll find out. Yeah, so here I've done a fritzing so that it can be built by others on a prototyping board. There's one thing about these STM modules is that these run at 3 volts. So in the prototype I've got a logic level shifter here because this LCD runs at 5 volts. But once I've done my PCB, everything will be running at 5 volts anyway. And then we've got this buck here that actually drops the voltage down to 1.5 volts to supply the caliper plug. So the way it works is we have our caliper, it's fed by 1.5 volts, that powers it up, and then it talks through a clock and a data lead which goes through these 2 transistors. What these 2 transistors do is bump up the 1.5 volt signals to 3.3 volt signals, which then goes to the microcontroller. The microcontroller takes that data, it converts it to an actual number that we understand, and then it outputs that number to the digital readout. It brings it out through the I2C bus, through the logic converter to bump it up to 5 volt logic, and displays on the screen. And also inside this, what the microcontroller does, it also sends the signal that we get from the caliper plug, and it sends it out to the out of the UART pins, which go to this little module here, which converts UART into USB. Then once it goes into the USB, it goes into my app, and my app does a lot. The actual signal that comes out of here is the raw signal from the caliper plug. What I'll do is I will do sort of like I'll show you what's coming out of the plug. So that goes into my application on the PC, and my application does its thing that I just showed you. So just give me a minute. Well, coming next. Oh, before I bring out the oscilloscope, for those that prefer a circuit diagram, here's the circuit diagram. Here's my STM8S103. It has the I2C output there that goes to the LCD, and it has the UART output there that goes to the UART, which is this thing here, and this UART sends it through to the USB. This is where I come in from the calipers, go through the 2 transistors for the logic level shifter, and this is a buck. This is a buck just to supply the 1.5 volts to the caliper, which is here, 1.5 volts. Yeah, there we go. That goes to the caliper. Okay, now I'll get the oscilloscope out. Alright, so here's my oscilloscope, and we can take a look at the data that's coming from the calipers. Now the data is inverted actually, because what I have, I've got the calipers. Where's my hand? Get my hand. There we go. We can see what I'm pointing at now. Right, so yeah, I think I've got the yellow trace going out of my data clock. Sorry, the clock, and the bluish. What is it? Magenta? No, I don't know what it is. It's bluish. Is the actual data, and you can see that we're getting a pulse every sort of like 90 milliseconds or 100 milliseconds. I think it's supposed to be 100 milliseconds apart. The thing is, it's going up and down because these isn't actually one pulse, it's a burst. That's a burst of data. And the reason I've got it inverted there is because I've actually got them connected to the outputs of the these two transistors. So we've got our clock, we've got our data, and they drive these two transistors here, which are pulled up to VDD, up to the power. So this is the 3.3 volts. So it's pulled high, and then we get a burst, which then pulls these two transistors low, and that's why it's inverted. So if we look at a burst, we'll just close in on one of these. Let me just set what my trigger's set to. Move my hand out of the way. I'll just put it there for a minute. Channel 2. Yeah, let's leave it on channel 2 on this one. Oh, and there we go. We've got it sort of, yeah. Oh, we want it falling as well, like so. We want. Oh, yeah, I've got it on fall. So why isn't that in the middle there? I have no idea. Oh, no, let's have it on manual as well, on normal. Oh, hang on, get this right. There we go. That's better. Right, so get rid of the menu. So yeah, so let's have a look at this burst here, shall we? Oh shit, I'm going the wrong way. Hang on. Yeah, that one. Yeah, so you can see it's a burst, actually a burst of two. Oh, let's move it across that way. A burst of two bits of data. So what's coming from the actual, this is the clock, so this should be just basic up down square wave. Let's just get a closer look. Move that back that way. Let's go to the first one. There, we should be able to see. Oh, I might have to zoom out a bit. There, we can see that there's 24 clock cycles in each one, so that's a 24-bit number. So every time it does a clock cycle, we read what the value here is, and it converts that into a value. So my software in the STM takes these clock pulses, checks the data, and finds out the number. Now this number, right, so we can look at this. So if we look at that, you can see that there's two actual 24-bit numbers there. They aren't actually the value that you see on the calipers. This value is a value that's read from the capacitance on the actual calipers. The calipers have like a row of capacitance plates along its length, and as the one of the caliper slides along the length of the caliper, the capacitance changes and it gives you a reading, and it's that reading that we're actually seeing here, which is a higher value than an actual millimeter or a thousandth of an inch. It's actually a higher number, so that you can have a more accurate division, if you get my meaning. So it's not the actual number that you're going to actually see that's sent from the calipers. This is just a 24-bit value that needs to be converted into either millimeters or inches. This value never changes no matter what you press on the actual calipers. This value is always a representation of the capacitance read from the actual microcontroller on the calipers. So anyways, so that's that. So you can see that we've got 2 bursts of data, well, 2 frames of data in each burst. So if I just zoom back out again, you can see that we're getting that burst every 100 milliseconds. Great time to buffer up there. So yeah, so every, well, it's that's a piece of crap there. Hang on, I'll zoom in a bit. Well, it's saying 200 milliseconds, but I'm sure it's about, yeah, actually I think it is 200. I don't know. It can't make its mind up, this thing. So yes, that's what we're reading, and that's what I'm converting. Now these actual numbers, what I'll do is I will let's try looking at them with a data analyzer. I haven't tried it with a data analyzer. I'm going to set it up and see what happens. Give me a moment. Alright, there we go. I've set up Pulse View and I have attached a data logger. So as we were looking at these pulses, you can see this is changing. These values keep going up and down, sort of thing. And we can't keep them. Well, I could just do one. Put it on manual, sort of like just put it on a single pulse, but and then we could actually just zoom in. Where are we? Zoom in and count when one is high and when one is low, every time that there's a clock cycle. But the easiest way is to use a data logger. And what we can do is we can grab these pulses into a buffer and keep them, and then we can zoom in and look at them. And we can also put in a decoder. Now Pulse View has loads of decoders. It doesn't have one for these calipers though. It has one for calipers, but it's not the one I have, because we'll have a look. So basically, if I just run this, it'll grab a few pulses from the calipers, and you can see the bursts there, which we can measure if we wanted to. So I've put them up, and what I can do is we can just measure between each pulse. There we go. Is that, no, not on there. Right, there we go, on each pulse, and we get sort of the time, and we can see there that the hertz is 3.1 or something, and where are we? What was it? Oh, 320 milliseconds. So yeah, well, something's not tying in there. Anyways, so I'll just get rid of that, and then what we can do also, we can zoom in on one of the frames, one of the bursts, and look at the 2 frames. And here we can see that I've put an encoder called caliper, and what it's telling me is this one says minus 26.8 inch, is it? What? No, we can't make my caliper in 20 odd inches long, you see, and this one is saying 16 millimeters. Now I know that these two things are not what these are. This one is for calibration and this one is for the actual digital. The Chinese have made it really simple. If it's a positive number, then you get a positive binary number, and if it's a negative number, you get an inverted binary number. That means the noughts will be ones and the ones will be noughts, and that's how you tell whether it's a negative. It's really simple, basically. So what we can do is we can look at these. These are our each clock, and every time there's a clock pulse we look to see what this line is, high or low, and if it's high then it's a 1, and if it's low then it's the other way around. But what I've done is I've used the SPI encoder here. It can be, you can tweak it to, well, SPI is serial peripheral interface, and you can actually, it's not always the same. Hang on, let me just show you. Right, you can actually change things, and what you're sending, I can tell it that a word size is 24 bits, and so it will treat the 24 pulse, first 24 pulses as a word, and so I've got a 24-bit word there, and if I was to change this, you can see that the encoder alters this bottom line here. Can you see where that is? Where's my hand? Can you see where that pointer is there? We've lost them 2 bits, so we're getting a different binary number there, and so on. What I'll just do is just change that back to 24. There we go. Now it's still not right because it's counting this first drop here, this first drop as a bit, and so we end up short here by 1 there. But it's the nearest thing I could find. I'll have to write one for this. But anyway, what you can see is we're actually converting it to ones and zeros. 1, and then we've got 0, 1s, and 1, 1, 0, 1, and that's basically a 24-bit binary number, and that is what we're using to find out what the value is. We don't convert this binary completely because this, like I was saying before, this number is a unit of the caliper. It's not a millimeter, it's not an inch, it's a unit of the caliper, and we need to convert that. So I just wanted to show you what's coming out of the calipers and what we're actually converting. So in my code I will convert that. I'll see if I bring some of my code up and see if I can show you what's going on. Right, I don't know if I'm going to explain this very well, but right, so we have our pulses. Well, we have a burst, and in each burst there's 2 frames. Each frame has 24 bytes, and that gives us a 24-bit number. But what we have to do is, when we're listening for bytes, is we have to make sure. Oh, right, yeah. So, because there's 224 bytes, every time there's 224 bytes, we have a low pulse, and then it counts 24 bytes. And each of these pulse, this clock, I have on a on my microcontroller. I had that clock pulsing on this PA3. So every time this clock pulses, or drops, shall I say, every time it drops, it goes it pulls this pin low, and so that I know that we need to read a bit of data basically. But what we have is we have a burst of 2 frames. Now there's no way of telling whether it's this frame or this frame that starts the pulse. What I could do is I could maybe miss that one, and I could start with that one, and that one, get that one, and then I would then grab this one, this first one. That would give me 2 frames thinking it's a burst. But what we need to do is to make sure that the first frame is this frame and not the second frame. So we count from there to here and then wait. So basically what we have, we know that we have a time between the 2 bursts. It bursts at regular intervals, and we know what that interval is. So what we can do is we can add a counter. So what I've done is I've added a counter. I've got my timer 2 that counts, and if that timer 2 does not get interrupted for a certain period, so a period at least this long, or shall I say longer than this period, as long as it counts for more than this period, I know that when we get another interrupt, we're going to be starting at frame 1 and then get frame 2 and so on. So basically in the code I have a counter that counts basically the interval, and then I have an interrupt handler on my port. So on this port here, which is port A, I am looking for this interrupt here. No, I am looking for this interrupt here, this every clock, and then when I get that clock pulse, I read what is on this pin here, and that gives me that value there. So once I get a pulse here, I will read what the value is here. Then when I get a pulse here, I'll read what the value is here. Then when I get a pulse here, I read what that value is. And I get a pulse here, and I read what that value is. And you can see below here that you can see that it'll either be a 1 or a 0, a 1 or a 0, a 1, a 1, a 1, a 0, a 1, until I end up with 24 bits to give me a 24 byte word. And that gives me my first frame. And so that's what my code here does. It logs that into my frame index. So my digital data is just an array with all those bytes added as each time we get a burst start, and then it reads 24 bits, get 24 bit count. I wait for the next burst again, and then all I do from there, if we get that, so that automatically goes into the buffer on an interrupt, so it doesn't actually go through the loop. Every interrupt, that buffer gets updated, and then once I go through my loop, no, forget that, my brain's on something else. But we just display the value. The value is in a buffer which is 17 bits long, because I'm only reading the relative display. That's only one of these. It actually only reads so much. I don't know why I did 17. Why did I do it? Oh no! Oh, sorry. No, it's 17 because this is going to be holding the actual number in characters. Although it's a 24-bit number, the actual number will only be probably 17 plus a null and a 0. It'll only be like 15 bits long, 15 characters long, shall I say? Yeah, 15 characters. Yeah, sorry. So that's where it all gets converted together, converted into characters. And then I sort of, what I also do here is my division is an integer division, which means I'm not using any floats. The float is sorted once I've got the value. I know where the decimal point is going to be when I convert it to a character, and I know whether it's going to be a plus or a minus, and I know where the decimal point is going to be. But all these characters are actual characters out of the ASCII characters. So my division is to get my division using just a integer and not a float, because it's only a small microcontroller and I want it to run quick, and I've got very little memory. It's best if all your calculations and your numbers and everything are actually integers. Yeah, that's the word I was looking for, integers. So to make your division into integer division, all I do is multiply everything by 2000. My raw number here is multiplied by 2000. So that basically what that is doing is doubling your number and moving your decimal place 3 places to the left, to the right, which means you end up with a whole number, and then you can divide whole numbers by whole numbers and get a whole number back, and you've got no decimals whatsoever, and so you don't need a float. So that's what I do there basically. To get that, that's my raw value there. So if I check to see if it's a negative or a positive, what I do is also we check to see if the binary starts off with zeros or if it starts off with ones, because if it's a negative value, the binary bits are actually inverted. So if we have let's try it down here. So if we have a binary number like say 1, oh yeah, let's have that there. What a negative number would be, let's see if it'll do it for me. There we go. A negative would be that. So you can see, let's just tab that across and tab that. There you go. So you see, a negative number would have the binary inverted, so you would have all where it would be a 0, it would actually be a 1, and where it's a 1, it would actually be a 0, and that's how it determines the 24-bit. Have we got 24? Yeah, we've got 24 bits there. I do love this. This is something new. This is Copilot. It watches it watches what you're doing, and then it takes a big guess at what you want to actually write. And more often than not with me, if you give it like a hint, negative, I typed in negative there, and it knew I wanted a negative of that, and it put it in for me. And it does all the work. After the time I'm typing code, I just press tab because it's done it for me. Oh, this is brilliant! Is this? I can't recommend it enough. This is another reason why, another plus for Visual Studio. I tell you. Anyways, I hope this might have been a bit of a boring video, but I hope some of it made sense, and you can see where I'm coming from to decode this. Hang on, I'll get my hand. So to decode this value, like I say, it's just 22. Now there are other protocols out there, and if you go on the internet and you read up, you'll find that some of them will say. Hang on, let's go down to this bottom one here. We can see it better. So yeah. What they will, which is what I think this converter is actually doing. What it'll say is that like the first 4 bits are flags to say whether it's a positive value or a negative value, whether it's millimeters or whether it's inches, and then the what is it? So that'll be the first 8 bits, maybe it'll be flags. That'll leave 16 bits for a number, and then it will be, or it may split. The first one is in millimeters and the second one is in inches. Well, it isn't. The Chinese are very clever. And basically all you need to know is a number. A number's a number. You just send a number and it's either positive or value, and since the number does not represent millimeters or inches, it's actually a raw value of the calipers units. Then all the calculation is done afterwards by your Windows software, which is basically what mine does. And so all my calculation is actually encoded in here. This might actually be better code to look at. I'll tell you what, I'll open up the code for this and have a quick view of that as well. Okay, a little bit about the software on the Windows side. Now, you don't want your software sort of just looping through, although it does loop through and through, but you want it scheduled, if sort of thing. You want it to be done every so often. So for that effect, basically I have a timer. So where's my timer? There we go. So I've got a timer that ticks. I forgot what that is. Let me look at the properties. Hang on. Oh, hang on. There we go. Timer properties. Yeah. So this ticks every 100 milliseconds, I think it is. And basically what I do is I don't have my interface sending data non-stop, going ping, 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 like the caliper does. The caliper just sends data ping, ping, ping. It just keeps, hang on, let's just have a look at this. So the caliper is constantly sending data. So if we just go to that one and we go auto, there, you can see that the caliper is just pinging bursts of data constantly, non-stop. But and my interface will actually grab all this data coming in, and it keeps grabbing it and grabbing it every time it receives some. But my interface will not be constantly sending data like this. What we do with Windows application is we ask for data. So what I have is a timer on my Windows application that asks the interface, and I've set it so that if I send an R command, I just send it down the UART through the serial. I send R. My interface will say, "Oh, you want some data? I will send it," and it sends it to it. And then what we do is we go to let's connect, let's receive. Oh, there we go, receive data. And so what we do is receive data, and we receive it in, we read the bytes, all of them, and then we get the bytes, and then we do oh yeah, it goes into a buffer, and then I think it's this one here, we display it here. And so we actually have the raw data coming in, which is not millimeters and it's not inches. Like I say, it's the raw data of the calipers, which is a unit of its own. and there are a lot of units in 1 millimeter, so that way you get the precision and accuracy. Yes, here we go. So basically we're dividing it by this number to get metric value, and we're dividing it by this number to get an imperial value. The raw value is the same. It doesn't really matter. It's a value of units. As long as you know what those units represent, then once you've divided them up by this unit, the reason why now I'm using a float. Well, actually, no, it's an integer, but I can use floats here because, well, it's on the PC. It's big. It's got lots of memory. It's got lots of processing power. Using floats is not a problem. But the fact is, the reason why I've multiplied the row here by 2000 is to get a similar. What can I say? It's to get a fraction. A fraction. It's to get more. It's to sort of get a lower division of the fraction. It's hard to explain. Basically, when you multiply stuff, you move the decimal place along again, and you can see that I'm multiplying it by lots here. 1, 2, 3, 4 zeros, and doubling it. And I double it because I want a value halfway between one of the caliper units. It's just so I can get a more accurate readout. It's when we're going down to these values here. Well, that's why I mean, you can see that we're going down to a tenth of a thou, but you can see the flickering up and down. You can see how accurate the calipers are. The calipers are only sort of like to within 10 thou, I would say, because these last two numbers are just bouncing up and down all the time. But this is the only stable number. Hang on, where's my hand? This is the only stable digit here. So we can say that our calipers are accurate. Oh, no, it's decided to call me a liar. We can say that our calipers are accurate to within 10 thou, because these are always going up and down, basically. Like I say, the right shape calipers. Yes, so I think I've just sort of waffled on about crap all, really. I don't know if anybody. I don't know whether to well, I'm in two minds to publish this, but if I published it and you've watched it and you've gained anything from it, good. But like I say, I'm not the best of explaining things, and I just tried to show you the workings, basically. I hope you just flicked through the boring bits in places, and if you actually watched to the end, thanks for watching. Well, I'm going to stop it there, guys. Thanks.